Hello and welcome everyone. So today's topic will be deep unsupervised learning for climate informatics. So machine learning applications to climate science, and I think today will be specifically about the problem of bias correction for global climate models. Our speaker is Claire Monteleoni. She is very well known in the climate informatics community. She was one of the founding members of the Climate Informatics Workshop and just launched a new journal, Environmental Data Science, I believe, which may be interesting to the audience. Claire did a PhD in computer science, I believe, from MIT, and spent some time in various universities, including George Brown and or George Washington, and Columbia, and is now an associate professor at CU Boulder. Her first work was actually with Gavin Schmidt, who's a very prominent climate scientist, essentially on weighing climate model ensembles using machine learning techniques. But since then, she's also expanded into different topics, bias correction. This is, I think, what we are hearing today, but also some work on solar forecasting for renewable energy, and also work on avalanche prediction, which could be very interesting as well. So with that, I'll shut up and hand it over to Claire.
Thanks for the kind introduction, Andre. Good to be back virtually in Toronto. So we study climate informatics due to the threat of climate change and the extreme events we've been witnessing, such as megastorms and heat waves resulting in wildfire and drought, and their effects on communities and ecosystems. And climate informatics is based on a vision that machine learning can shed light on climate change. Now, there's certainly a scientific consensus around climate change, but there are many open problems and large questions with a lot of uncertainty. And taking a cue from those pictures of extreme events, one thing that is highly uncertain and which is the subject of a lot of grand challenges in climate science is understanding how does climate change potentially affect the extreme events that we're going to observe. And the Intergovernmental Panel on Climate Change, in their fifth assessment report in 2013, kind of discussed, what was known and what is still uncertain. What is known is that there's been average warming. So if we look at average surface temperature trends since the 1900s, there has been warming. But they did this great summary for policymakers, and I heard that most of the people on this call are from data science, and so if you want to get a quick taster of climate science, check out the summary for policymakers from the IPCC fifth assessment report, where they take us through sort of an idea or like an intuition test to show where there's so much uncertainty. So let's go from what is known. We know there's warming on average. So that means if we look at just temperature as a random variable, say we'll assume it has a probability density function indicated in gray with some mean on the x-axis where temperature increases this way, then an average warming just means a mean shift to the right to a higher temperature. And an average warming alone would just give us this new probability density function, PDF, in the dotted line. And if that were the only thing that climate change meant, then we would then expect to see hot weather with higher probability and cold weather with lower probability, and on out into the tails. So higher probability of extreme hot, lower probability of extreme cold. Now, since there has been average warming, some of the changes that we're seeing might simply be due to this shifting of the mean in isolation, but we can't really think about this in isolation because this is a probability distribution, so we also have to think about the variance. Then they lead us through another figure that has us think about the variance and says, okay, so we start with some normal distribution for temperature, the same one that we started with before in gray, and even without a mean shift, what are the effects of higher variability? So if the variance increases in a normal distribution, you would get a normal distribution with heavier tails. That means higher probability of both extreme hot weather events and extreme cold weather events. So to understand the tails, we certainly have to understand variability, and here's where a lot of open questions lie. But also, as the IPCC acknowledges, this was sort of a very baby or toy way of thinking of it, by even assuming all this symmetry, etc. And really, there's an infinite number of possibilities of what the temperature distribution was and how it might change, to the point where there's many possible realities using asymmetry, where in future we'd see not only extreme hot weather with higher probability, but maybe about the same probability of seeing these extreme cold spells that we're seeing. So they sort of laid this out as a challenge problem to understand what's happening at the tails, at the extremes, to better understand variability, and especially at local scales. So we're data scientists, we're machine learners. Say we do want to study that. Say we want to study extremes. Well, by definition, extreme events are rare. That, of course, is going to give us class imbalance. Secondly, we just went through a set of scenarios to demonstrate that climate change, even for a single variable such as temperature, climate change may change its distribution, and thus the properties of the tails or the extremes of that distribution. So we're not going to be able to just use historical data and statistics computed from that to get robust future predictions and forecasts, for example, of extremes. But what's really unique about this as an application area, if you're a machine learner or a data scientist, is that there have been all these physics-based simulations of climate from the climate modeling community. And so when you model, millions of variables on a global grid evolving with time, you get into this massive high-dimensional big data setting. And of course, that's the setting that we like for machine learning. So there are some particular challenges with the types of data in the field of climate. Let me talk about that a little bit. So for the distant past, or paleoclimate, it's not so much of a big data problem as a collection of small data problems. So we have almost a sparse matrix over time and space, where in some locations we have a snapshot way back in time because we have a proxy for temperature and atmospheric concentrations via looking at a biological record, such as the rings of a tree or the growth properties of corals in the ocean, or things like lake sediment, where we can take a core under a lake and different species that are trapped are known to thrive under different nutrient and temperature conditions. And also, you've probably heard of ice cores, where you can get trapped air bubbles and use water isotopes to infer temperature and look at the gas inside the air bubbles. So these are great, these proxy records of temperature and atmospheric concentration, but they're highly sparse if we look over the whole globe. And that's all we have for the past. What we have in the present is massive amounts of very fine-grained measurements. So we're in what's called the observation era, where we have a very dense grid of measurements and all different kind of channels and bands of things that are being measured, both from satellites inside the ocean, balloons in the atmosphere, etc. So now we're in a massively high-dimensional data setting, and of course, in that setting, you may have to deal with lower intrinsic dimension than you're measuring at. And then, of course, it's also very time limited, because most of these measurements only came online in the past 100 or so years, several hundred years, getting more and more dense with time. But as I alluded to, what is super unique about this application area compared to other application areas where you might apply machine learning is that for over 40 years, scientists have been trying to simulate the climate. And these are computer-driven simulations that I'll talk about on the next slide. So on the plus side, they give us, massive data because we can treat the simulated data as input to our AI models. And on the plus side, these it's fake data, but it does encode domain knowledge about the physics and physical laws that need to be obeyed with all these climate processes. But on the minus side, any future prediction, of course, can't be validated, and things are not simulated exactly at scale due to different scale differences. So let me talk about that. So the goal of a climate model is to simulate these 4 systems: atmosphere, ocean, land, and cryosphere, so processes involving ice. And then each of these 4 systems then also have to interact with one another. But within a system, every single little process, such as heat advecting from the ocean, will be modeled using a mathematical model, so like a non-stochastic partial differential equation. And the reaction rates in these models are thought of as known. They're based on first principles in the related sciences. But if you think about this as a compute problem, it's far too large to compute at the real scale. So the climate will be simulated in grid boxes. They used to be at, say, 100 kilometers cubed resolution. Funding is being injected into some of these modeling programs to get to finer and finer resolutions, but it's still not fine enough resolution for all the processes, especially clouds and moist processes, to be modeled directly. And if you think about the computational challenges, there are some real challenges here in designing such a discretization, right? So let's just take the 2 systems of atmosphere and ocean, and let's first consider time scale. So the ocean circulates on the order of hundreds of years. The atmosphere circulates on the order of weeks. And so you have drastic differences in time scale that you have to kind of discretize or resolve over when you're coupling the atmosphere and ocean. And you have a similar story in terms of spatial scale. So I mentioned that clouds and many moist processes cannot be modeled exactly. That's because to actually model the formation of a cloud requires very tiny spatial scale, looking at whether water will condense around an aerosol particle. But you'll see in, say, your physical oceanography class that large packets of water and eddies can be modeled in the ocean without having to have a very tiny spatial scale. So drastic scale resolution differences have caused different teams to take different approaches, but in general, we can say that a climate model and even, say, a weather model, which we'll talk about later today, are outputting forecasts at some certain resolution, which might be more coarse-grained than what communities might want to do their decision making around climate risk. And I wanted to mention climate informatics, sort of this critical mass and community now that's been going for a decade. Actually, we turned into a conference and had our 10th iteration just last fall. And we have some upcoming announcements about this fall. And also there's going to be a residential program. If I can interest any of you data scientists, or if there's people already working in climate informatics, I'd like to invite you to our residential program in Santa Barbara for 7 weeks in November. So quick plug, check out the Kavli Institute website for more information. And looking back, about 6 years ago, when I was also trying to argue to machine learners to work on this problem, it was sort of like the early days of bioinformatics, where you can only predict the problems where machine learning could play a role, and machine learning already had played a role in some of these problems. But this is how we broke up the world back then as to where ML might have an impact. So I mentioned that paleoclimate reconstruction task. You have a massively sparse matrix over time and space with mostly missing data, but it's actually very important to be able to reconstruct past past climate to put current climate and future climate into perspective. Today I'm going to talk about climate downscaling, which is how we go from, say, a model prediction to something more finer scale. We've done a huge thrust on climate model ensembles. Andre alluded to that earlier, where we now have these physics-driven climate models, but since we also have observations, especially historical observations, can we use AI to do an intelligent ensembling as opposed to just taking the ensemble mean? Can we have adaptive predictions that actually learn the level of non-stationarity over both time and space? Space and time is a big theme here. So if you're interested in fields of data, I mean, you could also treat this as image data because you'll have, XY coordinates for your data, and then you'll have tensors that evolve with time. There's a big playground for that in this domain, and dependencies over space and time. So non-linear, non-independence, basically breaking the rules of most standard machine learning. It's a really interesting playground for that. And then, of course, I motivated the talk with pictures of extreme events. We've been pushing on that as well. I probably won't have time to talk about our work there today. But again, this was early days, and so especially for those of you located in Toronto or Canada, there's tons of climate scientists around, and I'm sure they would be really excited to talk to someone with your machine learning skills. There's lots of other problems that we weren't able to list. And then reflecting now in 2021 on what sort of the remaining bottlenecks and challenges are in applying machine learning. So as opposed to top-down climate science problems on the previous slide, this is sort of the bottom-up problems from a machine learner's perspective. And sometimes I'll talk about solutions, sometimes these are really just problems. We're really facing data limitations. So we're not typically going to have data that's labeled for a particular classification or regression task. And so that's why in this talk, I'm going to focus on unsupervised learning and sort of embedding or dimensionality reduction techniques. Andre mentioned briefly that we've done work on avalanche detection. So anytime you have a rare event, you're going to have severe class imbalance. And our avalanche work was how to address that using address not only class imbalance, but also a very limited amount of ground truth labeled data. And we talked about how to address that using unsupervised learning. But there's other issues. So bullets that I don't talk about right now, I'll talk about when I close the talk. I mentioned some of those scale resolution challenges, and we're going to address those in part by looking at downscaling. But my group, I think, has really the most work around non-stationarity. So we can't assume the data is identically independently distributed as you do in most intro machine learning theory books. And so we work on online learning where we're trying to learn the level of non-stationarity in the data. And we've contributed to doing this not only over time, but also both time and space. And then, of course, interpretability, which comes up along the way. And my group is particularly interested, since we're particularly interested in unsupervised deep learning and generative models, we're interested in interpretability of those generative models and the distributions that they can generate. So that's a lot. This is a short talk, and I decided to focus on unsupervised deep learning, where we'll also end up talking about self-supervision. In a longer version of this talk, I might also talk about a semi-supervised pipeline for the avalanche work. But I'm going to focus today on the downscaling work by request of Andre. And this is probably a general method. We did it for downscaling temperature, and then another experiment for downscaling precipitation. But this can be more general. And Yeah, so downscaling is where you have coarse-grained data, a coarse-grained spatiotemporal data field, maybe output by a model, and you'd like a finer-grained version of that field. So we're mostly machine learners here, so I'll mention this high-level idea meant to map from supervised deep learning to unsupervised deep learning. That said, if you're on the call and that's not your area, you can ignore this. We'll definitely go through the case study in more detail and motivation. But so just for those that this makes sense, let us abstract away our entire architecture, whatever set of activations and number of hidden layers and hidden nodes that we've chosen, into a function that can act upon an input and is parameterized by the whole set of weights and those decisions that were made in setting up the architecture in my capital W here. I hope people can see the mouse. Yes. And then I'll call the output of the network Y hat. So we know that to train the network, meaning to fit the values of these parameters W on training data, we want to do gradient descent on some loss function. So this is something that we can write down that we're trying to minimize. So the objective in learning would be to bring the output of the network close to the true label of our input image or vector X, which means that we need paired data or labeled data where we have example X and label Y. But assuming we have that, we write down the loss function that makes sense for the application, and then we do gradient descent on the loss function, or often stochastic gradient descent. And then the chain rule from taking derivatives will tell us the incremental updates we need to make to every single parameter in the network. Fine. The only change that you need to think about in unsupervised deep learning is that you don't have a label. So if you don't have a label of the data point, and this is true in many real world problems, you don't have very much ground truth labeled data, or maybe you literally just have a data source X and no defined label, then the only thing that means is that your loss function can't depend on some label Y. So let me just slightly change the notation to now call the output of the network an X hat. But I still have a whole network parameterized by capital W acting on an input. And as long as I can design a loss function that doesn't take some external Y, it could maybe also depend on the input and the output of the network, then I'm fine, because I can still just do gradient descent on the loss, and that'll tell me how to do the incremental updates to all the weights. So let's think about that for a second. What kind of loss functions don't need to depend on a label Y? Well, there's certainly now an emerging literature on clustering, where you can define loss functions on your whole training data set or also on mini batches that are designed to minimize some clustering objective, a K-clustering objective, a spectral clustering objective. There was a paper out a few years ago called Spectral Net, which is sort of like spectral clustering without the spectral clustering. You're just trying to train a network to minimize a spectral clustering loss. So that's certainly an application, and I'll just, or a direction that you could do unsupervised learning for. I'm going to talk more about unsupervised learning to learn some latent space. We often think of this as embedding or dimensionality reduction. But hopefully this should be very freeing. If you understood just the difference here, this should free you up to design a loss function, even when you don't have a label, and then still use deep learning, but unsupervised. So Andre said to go quickly on intro ML. And so I'll just basically say that, you know, what's an example of unsupervised loss function? Well, you could try to look at reconstruction error of the output of the network with respect to the input. And this seems to then be learning a very stupid machine. You're going to fit your weights in this part of the network, but the machine is sort of a noisy version of an identity function. That seems kind of useless. But remember that that's a pretext task, because after training on many instances and trying to get the output of the network to have low reconstruction error with respect to the input, of course, in an autoencoder, we'll get some latent representation of the whole training distribution that we trained on. I'm going quickly here, assuming that people are comfortable with a vanilla autoencoder. Typically, we'll send the data through a bottleneck layer, meaning that our latent representation is compact. It's lower dimension than the original image. But there's also wide autoencoders where you send, where the quote-unquote bottleneck is actually higher dimensional than the input or output. This is often the case, say, in cognitive science, where it's conjectured that the human visual system uses an overcomplete higher dimensional representation of its inputs in order to then have sparse representations for each signal. And then actually where we're going, the bottleneck will actually be the same size as the input and the output. But the only other thing I wanted to say here is you could train your autoencoder and then get a latent representation. But since we care about distributions, really we'd like to get a distribution over latent representations. And so you've heard of variational autoencoders. And as first introduced, they were going to fit a Gaussian over latent representations. So you start with some very simple prior, an isotropic Gaussian, then you can learn, the full covariant structure, or in this case, this is a spherical covariant structure, but you're still limited to Gaussians. And so we're going to want to get away from that and get even more informative distributions over the latent space. But understanding VAEs is a step towards understanding the next step. And then just a quick plug for unsupervised deep learning, semi-supervised pipelines, et cetera. This is what my group is looking at a lot these days. And had I had more time, I would have also maybe talked about the Avalanche paper. But check it out if you're interested. That was also in Climate Informatics 2020. And I'm going to talk about this downscaling task where it's unsupervised, but there's some self-supervisory signal, which is my understanding of how it works so well. And this is the work of Brian Gronke, who did his master's in my group in computer science, and then went on and is now a PhD student in Potsdam at Alfred Wegener Institute, which is a climate informatics lab. So downscaling, as I said, problems come up across climate and meteorology. I believe Andre had a different word for it. So yeah, he's definitely the climate domain expert. But especially for machine learners, I need to warn you that up and down kind of have different meanings in machine learning versus climate. So we might think of upsampling or super resolution to mean the same direction as the word downscaling in climate and meteorology, which means go from coarse-grained to fine-grained. And actually, the method that we propose can actually go in both directions, so it's maybe less of an issue. There's a field of statistical downscaling. From a machine learning perspective, when we looked at the existing work, the methods were supervised in that if you wanted to train a statistical downscaling method in the literature, you would need paired data, meaning for a given spatiotemporal field, you would need instances at coarse-grained and fine-grained. You would need maps, two maps, one at the fine-grained scale and one at the coarse-grained scale that correspond to one another. And you would need to train with many of these pairs. So we don't want a supervised method. And also we want a generative method. So these methods, once trained, you could give them a map at coarse resolution and the method would output a map at fine resolution. But we view that, even though it's a whole map with values at different grid points, we view that as a point prediction as opposed to a distribution or probabilistic prediction. So distribution over such maps at the finer scale. So we instead wanted to do generative downscaling, which was open as far as we were aware in the application domain. And so we appealed to this machine learning task called domain alignment, and we're able to adapt some recent works in deep unsupervised learning for domain alignment. And I would definitely encourage you to go and read the align flow and GLOW papers in further detail. The punchline is that that's what we did, and then we obtained a generative model for downscaling. I'm going to go a bit more into detail, but just to understand the message here, my understanding as to how this works is that, as to why this works, is that there is some self-supervisory signal via the fact that even though we don't need pairs of images at fine and coarse grain scale, we just need access to samples at either scale. The bounding boxes of these maps were aligned, so there was geographical alignment, aligning sort of the physical processes, which would, relate the data, since the underlying physical processes are related. So there's some, I would say, spatial self-supervision that allowed these methods to work well. So downscaling is just going from coarse resolution, here's 1 degree lat-long resolution, to fine resolution, say 1/8 degree lat-long resolution. We did this both for temperature and precipitation. What's interesting is that it doesn't really matter what the data source is. And, when Andre was introducing this talk, he kind of motivated it as taking the output from climate models and getting it to more local scales. I actually motivated it that way myself, but actually we're going to use physical models, numerical weather prediction models, WRF in particular, to give us our fine-grained data set, and we're actually going to use observation data actually passed through models for smoothing, known as reanalysis data from the ERA interim data set, as our coarse resolution data. So you could have data from completely different sources and completely different generating processes, but corresponding to the same field. So ERA can generate a temperature field, it can generate a precipitation field, and in both cases, we took those at a coarser resolution than we took the output of WRF, the NWP model. So the domain alignment task is where you just need to have IID access to the marginals of 2 different random variables. And the goal is to learn a bijection F, so that with samples from the marginal of X, applying F will allow you to approximate the marginal of Y. And similarly, given IID samples from the marginal of Y, applying the inverse of F will allow you to approximate the marginal of X. So we can go away from the traditional machine learning interpretation of X and Y as example label. These are just 2 different random variables. And for our application, right, one would refer to the distribution over maps or fields of, say, temperature at coarse resolution, and the other would refer to the distribution of the same quantity at fine resolution. So ideally, if we want to be able to up or downscale and go, symmetrically in either direction, we would like to know the joint probability density function over the coarse scale and the fine scale data. So the idea of align flow, which came out in last year's AAAI, is to assume that these 2 different random variables, and so in our case, granularities, are conditionally independent given some latent space. So that's what Z is on the right-hand side. So if you add that conditional independence assumption, then that helps you just get back to the full joint over the 2 domains and the latent space. And then, of course, you can integrate out the latent space to get the joint that you were after. So the align flow method is how we're going to model our conditional distributions of each field given the latent space, which will give us then a shared latent space. And I'm going to talk on the next slide about normalizing flows, but what's important to remember is we can still start with a very simple prior, an uninformative prior on the latent space, but via a normalizing flow, we can learn something much more informative than just, say, a Gaussian, as you would in a VAE, as our distribution over this latent space, which shares the information between our two different data domains, coarse-grained and fine-grained. The take-home message for practitioners, or also people that want to see why this is unsupervised, is that you never need pairing between examples from the two domains. You just need to have IID access to each of the marginals. So normalizing flows kind of improve upon VAE because starting with an uninformative prior like a uniform or a isotropic Gaussian, you can compose a series of transformations where you learn the parameters of these transformations, and what's important is that they're invertible to get much more informative distributions over your latent space. So these are visualizations of some of the flows from the original normalizing flow paper, and we're going to learn one normalizing flow to connect one data domain to the latent space, and another normalizing flow to connect the other data domain to the same latent space. As you can see here, so we'll have one domain, the other domain, and the shared latent space, and the only part that is learned are these flows. That's where the parameters will need to get fit. And instead of using the exact original version of the flows in a line flow, we used GLOW, which is a normalizing flow implemented by one by one invertible convolutions. So at a high level, the parameters that we need to learn in the network will give us this sort of bijection between one of our data domains and the latent space, and then a separate set of parameters to learn the flow between the other data domain and our latent space. Now, I said we're not going to send anything through a bottleneck. We're going to, in terms of the architecture, use the same size representation in the latent space as our highest resolution data domain, which means for the low resolution data domain, we have to upsample or just fill in values so that we're representing it at the same dimensions internally. But we do that without in the way that adds the least additional information. So we just look at neighboring pixels to smooth in the pixels to get us to the right dimension. So the only thing we could do quantitatively, we did some cool qualitative stuff, is a whole bunch of experiments. These are just some of them. We also used a lot of the ClimDex climate index tests. But all these experiments are only comparing to supervised methods. And to compare to supervised learning methods, we have to do so on paired data. And the supervised methods were trained on paired data. The unsupervised methods were not. And so we're not going to be able to expect the techniques, the unsupervised techniques, to perform better than the supervised techniques, but it doesn't perform much worse. So BCSD was the state of the art in downscaling. I don't think it's even a machine learning method. Banyo Medina was a CNN approach that came out in the previous year's climate informatics, where they applied a CNN in a supervised way, where again, you'll have a paired low resolution and high resolution image for the same data field, and you'll have many instances of those. So we were able to, get a table like this by testing on labeled data, i.e. paired images at low and high resolution, and we're only going to here be able to report RMSE, et cetera, correlation on point predictions, which is that once the model is trained, you take in a high resolution map or coarse resolution map and output a fine resolution map. But it's comparable, not that much worse. what is the strength of this method, though? It's generative, right? And those previous methods were not. So how does the generative, how could we evaluate that? We could, okay, so I'm wrapping up, just a couple of results slides. So we could take our coarse-grained input image. This is, precipitation coming out of ERA at 1 degree scale. The paired image for this test was this one, and the model is not given that. It's just given the one on the far left, and it outputs the one on the far right, circled in gray, as its predicted fine scale precip map. But then, of course, conditioned on that input image, you could sample as much as you want and get like a whole distribution over fine-grained precipitation maps from the method. The other cool thing that I'll just mention, and especially for machine learners, you're probably aware that now with these latent space learning methods, there's interest in visualizing what happens when you interpolate by walking through latent space. Now, there's a whole literature on how you should do this walk. Ideally, it's along the geodesics of the posterior distribution you've learned over your latent space. And so here, it's actually, so it would be called upscaling for climate people, but I guess down sampling for machine learners. We started at the fine resolution. So the inputs are just the far right and far left images on the top row. So that gets mapped to the latent space. We can then output a coarse resolution image for both of them. Then from the latent space points that they're each mapped to, we can walk in the latent space to get a latent space interpolation. And then at each point in our interpolation, we can output an image at a fine scale or coarse scale. In terms of interpretability, these input images were WRF simulations at 2 different times. So you could view this as some version of a temporal interpolation, which you can see at fine scale and coarse scale. So I'll wrap up. We're doing quite a bit these days around extremes. We have work on looking at temperature and wind fields around the track of a hurricane, and then looking at its past track to try to forecast locations, and ended up getting techniques that were competitive with state-of-the-art. Avalanche detection, have done stuff around precipitation extremes in the monsoon, which are extremely hard to predict. And also just general approaches that show that unsupervised learning can be a good way to learn sort of probabilistic representations for multivariate extreme events, instead of just having to threshold one variable or another, or look only for drought or only for a precipitation extreme. You can use unsupervised learning to find multiple extreme events simultaneously using multivariate data. In terms of outlook, we talked about kind of the first bullet under data limitations. The class imbalance bullet we talk about or deal with in our extremes work, especially I thought it was sort of interesting what we did for the avalanche approach. My thought now, though, is, or one direction where I'd like to see things going, is that, as I mentioned, the observation era is very limited in time. We don't have a lot of diversity and granularity over the time dimension, at least on the order of years or decades. And there's no counterfactual world, so we can't just make a change and test how that works, because we only have the climate that we've observed. So the idea is sort of use the spatial diversity and granularity that we have of data, which can actually be highly granular these days, sort of as a proxy for what we're lacking in diversity and granularity over time. there's issues, I mentioned at the beginning that moist processes are not being modeled in the climate models, and climate modelers are looking to machine learners to help with that. It's not an area that I've worked on, but it's very important. And then, yeah, if you're interested to check out our other publications on learning, and we've shown that these can be used also for things like finance, any domain that's non-stationary. And finally, interpretability is really important. Thank you.
Yeah, thank you very much, Claire. That was an excellent talk, especially the introduction in the beginning, I think, was very informative for our audience, and many will appreciate that. I personally have a couple of questions. I encourage the audience to post questions in the YouTube chat. We already have one, which is basically just a technical question, and that is in your unsupervised learning techniques, how did you formulate the loss function?
This is the loss function, which is directly from the align flow paper. So there are these sort of MLE losses on each of the mappings, and then there's sort of a actor critic style loss. Let's see, what is C? I have to double check. Anyway, I will refer you guys to either Brian's thesis or to the Align Flow paper for further details on it. But just like sort of any other of the sort of modern day versions of flow or variational autoencoders, there's going to be, some kind of regularizer and some sort of loss based on fitting the data.
So if I may briefly ask, the Gan loss, that is something where you trained an adversarial network for. Is that correct?
Yeah, but this is actually, I think, more of like an actor critic loss.
Okay.
I think, don't quote me on it. I refer people to the Align Flow paper for details. We did nothing beyond Align Flow with the loss. What we did do differently was we used GLOW for normalizing flow.
Okay, that is also something I'm not familiar with.
So GLOW, that's a 2018 paper where they showed that you can define these one-by-one invertible convolutions. And they were able to, at least in 2018, get much more impressive results using these normalizing flows generatively for things like faces. So we just picked it because it was working really well.
Okay, so a lot of this machinery that you've used actually comes from face recognition, or?
So let's see. I'll just refer you to the actual. These are the two papers that you're going to want to check out.
Right. Okay.
I believe this paper was in AAAI, and I think this one is in ICML. No, so it's sort of along the lines of usually GANs are what are used to generate things like fake celebrity faces.
Right.
But they it's very hard to evaluate their distributions that they generate. You can't go in and interrogate the latent space because there's no latent space representation in a GAN. And so people have been seeing if they can take something like a VAE and improve it to where it can be used generatively to generate, good faces or what have you. Those are the test cases that are used in ML to show that something works. And so GLOW, which is a normalizing flow, can generate good images. But in our case, we're going to be. So ultimately, once you've trained this model, how can you use it? You could sample conditionally, as we've seen. We can input a low resolution say, temperature map all the way through, and then output a high resolution temperature map. But actually, when we map through, we can then sample P of Z given X as much as we want conditionally, and then ultimately P of Y given that Z. So we can get as many conditional samples as we want in both directions. The other thing I don't think I mentioned is that we could sample unconditionally. We've now learned a distribution over a latent space, so we don't even need an input image. We could just sample from this informative distribution as much as we want and generate fake temperature maps at low and high resolution.
So you could essentially use it as a weather generator, right?
You can use it generatively, yeah.
Yeah. This is actually something that is quite often used in hydrology to generate small-scale variability. Yeah. There is a market for that. Essentially, people use it in a similar way as you do, in that they take projections from GCMs, and then they just use a weather generator for the current weather, and then just sort of add changes from the GCM to the randomly generated weather. It's a very similar idea. The problem there is always that they are fairly constrained what the distributions are that they can use. So most of the things are either exponentially or normally distributed, and the autocorrelations or the correlations between variables are actually quite poor, and which I think in your latent representation, the covariance structure would be much better represented or learned, right?
Yeah, that said, the question I always get from real domain experts is about the interpretability of the latent space. And I think that's something that's of interest, even just in core AI research, is like I mentioned that for interpolation, there's now a whole line of work on how you take this walk through latent space. And now that you've learned potentially highly complex and therefore informative distribution over your latent space, how do we interpret that, even just for defining how you take a walk in latent space? And the more complex your distribution is, the more complex the geodesic path would be along that distribution. And then we also have to take into account computing issues of computing that the path that is most faithful to the geodesic is actually computationally expensive. So there are different approximation techniques that manage that trade-off between faithfulness to that distribution that you've learned and walking along its path versus being easy to compute.
This actually brings me to another question I had as a practitioner of sorts in this area. If I wanted to apply this method myself for downscaling of climate projections, what kind of computing infrastructure do I need? How expensive is this?
So we had Google Cloud credits. I think Brian burned through an entire research grant of cloud credits. But you can grab the code here on GitHub. And yeah, you might need to use a cloud resource. I'm not, I don't have real numbers on complexity. Yeah. I don't know if he ran such tests, but if he did, it would probably be in the full version, which is in his master's thesis.
Right. Okay. Good. That's good to know. The training set data you used with Erler Interim and WRF, how long is that? How many time steps did you use for training?
Sorry, I'm not sure about that either. Okay. Let's see. Oh, though there is one cool thing though that you might find of interest. So just like we took our liberty to use actually completely different sources, right? We've got reanalysis data, which comes from observations originally, and then we have the output of NWP. Brian was also interested in whether you could actually mismatch your fine and coarse grained resolutions in time. which seems like kind of a bad idea from the physical perspective. But actually, our methods still worked pretty well. And
for
the
training
idea,
mismatch or in
well, we don't need to train with pairs. So
right,
it's not a
exactly.
question of taking pairs that are mismatched. But when we have our marginal distribution over high res and low res data, those could be taken from different time periods, actually.
I see. Okay.
And it actually still worked fine. So I think the idea is that this might change the distribution you get over your shared latent space, right? But right, the method doesn't really care about that.
Yeah, and it would indicate that you don't need that much data to be able to learn these distributions, right? It seems fairly robust.
I think you actually do need a lot of data. I mean, the key assumption that, of course, you might break in practice, though, is that you have IID samples at both resolutions, and you need a significant amount of each of those.
Right. So you need to space it a little bit so you cannot take time steps too close, right?
Oh, well, yeah, because then you're not going to have a lot of diversity.
Right. And they're not going to be really independent. Yeah. Okay, good. I think we have to wrap up here now. You told me you have to leave by 1, so I'll let you go. Thank you very much for the presentation.
Yeah, thanks.